When the forces of nature, the anger of the sea, the fury of the wind, or the grinding cataclysm of an earthquake encounter man's works, disaster often ensues. But nature is not the only destructive force. Following disaster, man must restore, but his efforts are often hampered by the absence of that modern-day genie, electricity. Recovery from such disaster is highly dependent upon supply lines and availability of electrical power, long-term, reliable, self-sustained power. To meet the challenge of these requirements, the Corps of Engineers conceived the MH-1A floating nuclear power plant. This concept provides mobility by mounting a 10 million watt electrical power plant on a seagoing barge. A nuclear reactor heat source eliminates the need of a continuous supply of fossil fuels required for the non-nuclear power plant. This power plant, traveling the oceans and inland waterways of the world, can bring electrical power to any point accessible to ocean-going vessels of moderate draft. The basic concept was developed into a detailed specification by the Corps of Engineers at Fort Belvoir. Preparation of the specification was in itself a big job. The specification requirements highlights are these: conversion of a World War II Liberty ship to a manned, non-propelled barge for ocean service, inspected and certified by the United States Coast Guard. 10,000 kW net electrical output. High availability. Refueling once a year. And a 1-year supply of onboard repair parts. To give substance to the floating nuclear power plant concept, the Corps of Engineers selected the nuclear division of the Martin Marietta Corporation as prime contractor. The contract was let by the Corps of Engineers Philadelphia District Office. The prime contractor, in turn, selected the J.J. Henry Company, Incorporated, as subcontractor for naval architecture, and the Alabama Dry Dock and Shipbuilding Company as subcontractor for construction of the vessel. The program was divided into phases, designated A through H, and was contracted for by these phases. Phase A, contracted in September 1961, provided a 1-year period for development of preliminary design drawings and equipment specifications. This phase was completed on schedule and was approved. Phase B, contracted in January 1963, included preparing final design drawings and equipment specifications, obtaining required Corps of Engineers, Coast Guard, U.S. Public Health, and American Bureau of Ships approvals and certificates, procuring and fabrication of equipment, converting the Liberty ship into a barge, installation of power plant equipment, such as the steam generator, performing dockside testing using a non-nuclear heat source, and towing of the MH-1A to the operational test site at Fort Belvoir. Under Phase C, the low-enriched 2,932 kilogram uranium dioxide core was built and tested in the prime contractor's critical facility. Following completion of Phase B, which concludes with inspection at Fort Belvoir, the MH-1A floating nuclear power plant will be subjected to operational testing and will then be accepted by the Corps of Engineers. Testing and acceptance are under Phase D. The logistics efforts, repair parts, technical manuals, and training are under Phases E, F, and G. These phases began during the Phase B construction time span and will extend through acceptance of the plant. Phase H is the requirement for this documentary film. The film is in 2 parts. You are viewing the first part covering construction. The second part deals with dockside testing. The 2-part film was made during Phase B time period and therefore does not cover Phase D, operational testing and acceptance. With negotiations and other paperwork concluded, it was now time to get to work on construction. After a thorough inspection of ships in the Maritime Administration's Mobile Reserve Fleet, the Liberty ship Charles H. Kugel was chosen because of the soundness of her hull. Removing the Kugel from the fleet and towing to the shipyard were the first milestones in the ship's new career. At the shipyard, she was put into dry dock, and the conversion work began in earnest. The first major step in conversion was construction of a new mid-body. The insertion of a new mid-body was chosen instead of the alternative using the existing mid-body. A noteworthy feature of the mid-body is the collision barrier. This barrier incorporates heavily reinforced structure to limit penetration of a colliding ship to a point short of the nuclear component area and to prevent transmittal of collision shocks to the nuclear components. During mid-body construction, the concrete secondary shielding for the nuclear plant was installed. The resulting concrete structure is of massive proportions. It extends around the entire nuclear plant in thicknesses ranging up to 48 inches. Its approximate weight is 800 tons. As the new mid-body neared completion, the bow of the Kugel was severed, and the old mid-body and stern were removed from the dry dock. The big day, launching, arrived for the mid-body. Interested observers arrived early to reserve choice viewing spots. Preparations for launch were completed. The launching trigger was tripped, and the mid-body slipped from the ways. The first stage of the mid-body's waterborne career was very short, however. Tugs took the mid-body under tow and departed for the dry dock. At the dock, the new mid-body was positioned for splicing to the old bow, and the dock was raised. With the dry dock bearing the mid-body and bow raised, work on splicing the ship's sections began. Then followed in sequence, removal of bow and mid-body from dry dock, return of stern and old mid-body to dry dock, separation of the stern, removal of old mid-body from dry dock, positioning the bow and new mid-body in dry dock, and splicing to the stern. For greater maneuvering capability while under tow, a larger new rudder was installed, and the old steam-powered steering engine was replaced by an electro-hydraulic unit. Construction of the hull was completed, and it was made ready for removal from dry dock. Hull statistics are length 441 feet and beam 65 feet. At completion, the vessel's draft will be approximately 18 feet. Here we see the reverse contour of the mid-body extending beyond the original lines of the ship. This added beam was necessary to accommodate the nuclear plant containment vessel, shielding, and collision barrier. Note also the large opening amidship. It is this area that will receive the nuclear plant containment vessel. The hull, removed from its dry dock, had lost its identity as the Charles H. Kugel. It was now a new ship, the STURGIS, but was not yet the MH-1A. The tide would rise and fall many times before the floating nuclear power plant concept came to full fruition. Concurrently with the work on the STURGIS, construction of the containment vessel was completed at a steel fabricating plant in Baton Rouge, Louisiana. This ovate structure, housing the nuclear reactor and other high-activity, high-pressure components of the primary plant, prevents release of radioactive materials to the atmosphere. The vessel was built at a point approximately 3/4 of a mile from the Mississippi River. It was necessary to move the vessel overland to the levee, load it on a barge, and float it to New Orleans for installation in the STURGIS. The installation was made in that area because it was there that the nearest crane was available that could handle the huge vessel. The overland move was made on a specially constructed trailer. The weight and size of the vessel, 350 tons and 31-foot diameter by 44-foot length, made careful planning and preparation for transport vital. Utility wires and other obstacles had to be moved, and normal highway traffic had to be halted during the move. At the time the vessel was transported, it was the largest and heaviest single component ever transported over a public highway. Other preparations completed, the powerful highway tractors that would furnish motive power were coupled to the trailer. Track-laying vehicles were temporarily coupled ahead of the tractors to provide added initial tractive effort. And the giant moved out. During the move, in all areas of questionable foundation, a temporary road was made by placing huge overlapping timbers for the trailer to roll on. And the approaches to the river barge were prepared. All was in readiness when the vessel approached the barge. The vessel, on its transport and with the motive power units, was moved onto the river barge and was secured for the downriver voyage. At the New Orleans rendezvous with the Sturgis, the containment vessel was lifted from the barge, and the Sturgis was positioned beneath. When the containment vessel was secure in the hold, the Sturgis returned to its home shipyard at Mobile to have the power plant equipment installed. This scale model of the containment vessel and its installed equipment was developed concurrently with vessel design. It served as an engineering tool, helping to solve arrangement and installation problems, and aided in checking drawings prior to the actual construction. The primary plant consists of the nuclear reactor and associated systems and components necessary for its safe operation. For reliability purposes, the primary plant design employs a proven state-of-the-art approach. This permits the MH-1A to be a truly operational power plant rather than a developmental one. Therefore, the system consists of the somewhat conventional pressurized water system components and coolant loop. The thermal energy from the reactor is transported by the coolant through the primary plant in piping to the tube-type steam generator, exchanging heat from the reactor coolant system to secondary system water. The loop is completed by coolant piping back to the reactor pressure vessel. Two coolant pumps circulate the coolant. A pressurizer connected to the reactor coolant loop by a surge line accommodates system volume changes and maintains system pressure within safe limits. Let's examine these vital components a little more closely as they are being installed within the containment vessel. The reactor assembly is housed in this shield tank. Ion detectors, shown here being protected for cleanliness, are around the reactor. Cooling coils around the shield tank maintain shield water at correct temperature. The reactor assembly, surrounded by the shield tank, consists of the pressure vessel, core barrel, core, and control rods. Primary shielding of lead surrounds the pressure vessel. The pressure vessel is fabricated from type 316 stainless steel. It is approximately 15 feet long and 6 feet in diameter. Its design pressure is 1600 psia. However, it was hydrostatically tested at 2625 psia. Built to rigid specifications, this vessel carries a U.S. Coast Guard certificate of approval. The core barrel, which properly aligns the fuel elements, supports them, and channels coolant flow in and out, was fabricated and then shipped to the pressure vessel manufacturer for fit-up verification. The core barrel was then returned to the prime contractor's licensed critical facility, where the 45-megawatt thermal reactor fuel elements and control rods were loaded in its lower half. The fuel elements were loaded on 12 April 1965. The loading was completed in 6 hours. Alignment checks were then made and reactor criticality tests performed. The reactor went critical on 20 April 1965. After testing, the fuel elements were shipped to Fort Belvoir, Virginia. They will be installed in the MH-1A during the performance test phase that will be conducted at that site. The core barrel was sent to the shipyard, where it was installed within the pressure vessel. The 12 rack and pinion type control rod actuator pressure thimbles were assembled on the pressure vessel head at this clean area. This assembly was then placed on the pressure vessel and was precisely aligned by use of optical instruments. The drive motors were installed to complete the assembly. These 12 actuators drive the control rods to the fully inserted position at 2 inches per minute in normal operation. At a scram, a minimum of 8 inches of travel occurs within 1/2 second. The actuators are operated automatically under scram conditions. Thus, the reactor will be rendered subcritical even in the unlikely event of capsizing. This feature has been tested with the actuators in the inverted position. A buffer seal system controls the coolant leakage through the actuator dynamic seal. Coolant leaves the reactor outlet nozzle at approximately 510 degrees Fahrenheit and is transported by this 12-inch stainless steel piping to the steam generator. The piping contains no flanges, thus no leaks. All All welds were dye-checked, radiographed, and ultrasonically tested to verify quality. A loop seal is formed by this inverted elbow. Its shape permits thermal growth of the piping without undue stress. Its height allows drainage of the steam generator and the coolant pumps without uncovering the core, even at a list condition of 15 degrees. The secondary shield, in addition to the concrete seen earlier, consists of lead and polyethylene. The secondary shield is constructed close to the forward end, sides, and top of the containment vessel. At the after end of the vessel, however, the concrete shielding extends well aft of the vessel, thus forming the reactor access compartment. In this compartment is the radioactive waste disposal system. Liquid wastes are collected in 2 tanks of 6,000 gallon and 10,000 gallon capacity and are processed by evaporation or dilution to render them safe. Following processing, the condensates of evaporated wastes are returned to the operating system or discharged overboard. All dilute waste is discharged overboard. Gaseous wastes are filtered, compressed, stored for decay, and released to atmosphere when the activity level is within safety tolerances. Also within the reactor access compartment is this 24-foot, 7,500-gallon spent fuel storage tank. Both the secondary shielding and the containment vessel have many penetrations to accommodate power cables, instrumentation and control cables, service system connections, this main steam line from the steam generator to the steam electric conversion plant, and the return feed water line. At full reactor power, the main steam line carries over 170,000 pounds per hour of dry, saturated steam at a pressure of 327 pounds PSIG. This flow rate, along with numerous other plant functions, is monitored on the control console in the control room. A small part of the steam flow, about 6,000 pounds per hour, is used in auxiliary service by units such as the hotel service heat exchanger, the turbine-driven standby feed pump, and the standby lubricating oil pump. For auxiliary services requiring steam at less than main steam pressure, pressure-reducing stations are installed. The main steam flow, approximately 164,000 pounds per hour, drives the turbine generator. Turbine speeds of 3,000 or 3,600 RPM may be selected to produce 50 or 60 cycle per second power. The plant is thus fitted to the needs of most localities throughout the world. At 50 cycles, the turbine generator normal output is 9583 kilowatts at 11,500 volts. At 60 cycles, the normal output is 11,500 kW at 13,800 volts. Ship service electrical requirements are supplied by the turbine generator. When the plant is operated at 50 cycles, a frequency changer converts to 60 cycles the electrical requirement for powering the shipboard electrical demand. Power from the turbine generator passes through the switchgear to the transformers to the ship's transmission tower. A shore transmission tower is stowed in the ship's hold. At operating sites, this tower is erected on shore, and cables are strung between it and the ship's tower. Submarine transmission cables are also provided for situations where use of the tower is not practicable. Net output to the shore is 10,000 kW. A part of the steam employed by the turbine is extracted in 3 bleed stages and is used again for operation of auxiliary equipment such as feed water heaters. The remainder of the turbine steam goes directly to the main condenser. The condenser has 2 compartments, each of which can condense 75% of the steam exhausted by the turbine at full power. The steam enters the shell side of the condenser and is cooled by raw seawater from the traveling screen well. The raw seawater is circulated through tubes in the condenser by the main circulating pumps. The condensate formed in the condenser shell returns to the steam generator through the feed water system. Control and monitoring of plant operation is centralized in the control room. Here are the instruments and controls that keep watch on the plant's pulse and supply remedies if that pulse changes pace. The operator was kept uppermost in mind when the layout of this area was designed. The contractor worked in conjunction with the Army's Human Factors Engineering Section of Aberdeen Proving Grounds to arrive at the best possible layout for operator convenience and efficiency. Ship service power needs are supplied by the primary plant during service operation. But since the primary plant does not operate while the MH-1A is under tow, another source of power is required. Diesel generators furnish the power. These diesel generators also furnish the power needed to start up the nuclear plant. We have now seen the essentials of construction of the hull and installation of the power-producing equipment. But there is more to the ship than this. Decontamination and radiochemical laboratories were installed to ensure safe handling and analysis of radioactive materials. Safety devices also include firefighting systems and equipment, radiation monitoring equipment, the reactor safety system. The bridge had to be equipped, and the facilities for life aboard ship were provided for the towing crew of 15 men. A big factor toward low logistics requirements is the machine shop. A one-year supply of spare parts was stowed, and the ship's outfit was brought aboard. Cranes were mounted, and the vessel's insignia and name were affixed. The Sturgis was now ready for her first step as a unit toward her ultimate career. This step was dockside testing. The tests verified proper installation and operation of all equipment and systems, but did not include reactor critical testing. The reactor will be tested at Fort Belvoir. The dockside tests range from proving the functioning of refueling tools to incline testing of the ship. After completion of dockside testing, which is covered more completely in Reel 2 of this film, finishing touches were applied. Finally, a general inspection was made. Inspection completed, this first of a new breed of floating nuclear power plants left her birthplace. Her next career milestone, installation of the reactor fuel elements and operational testing, would be passed at Fort Belvoir, Virginia, and she would be the MH-1A Sturgis.